Hey guys, Sándor here from VQ-VAE, and in this episode we are implementing the soft VQ-VAE, the soft vector quantized variational autoencoder, which is a research paper from 2024 December, last revised 14th March 2025. So this is pretty new, and we're not implementing the full paper, but it's just such a fun solution and it's so easy at the core that please refer back to my previous video about the VQ-VAEs, because I'm going to use the same Python notebook, and we'll just remove lots of it and basically add a few lines of code, and we'll arrive at the soft VQ. So let's get to it. And this was the last reconstruction. I added the group norm in the end, which I will revert now here because it wasn't so great. Select the kernel. And we did lots of stuff with the VQ. We calculated codebook loss, commitment loss, we added them together, calculated perplexity. During training, we calculated the codebook usage, and based on the codebook usage, we refreshed our codebook periodically. We also needed to initialize the codebook based on the encoder output, and so on and so on. Now the difference between the standard and the soft VQ is that maybe it's just better if I show it in the code. When we calculate, let's go to the vector quantizer. So when we calculate these distances, we treat them as probabilities using a softmax. And by using that, we do not limit ourselves to our fixed size codebook, because the distances will determine how with what probability or to what degree that codebook is used. So it becomes the quantized vector that we feed to the decoder becomes a combination of this codebook, thereby increasing the latent space radically that we can use. And also it's much faster, and we don't need to deal with the codebook loss and so on. So first, we are just cleaning up our codebook. Perhaps the best to start is to remove the codebook use. Let's change this to a uniform initialization. -1 per self.k and +1 self.k. I'm going to remove the comments mostly. And now we don't need this part. And actually we can remove all this shit. We won't have VQ loss. We will write the new code here. We don't need to initialize our codebook because the uniform in it will be fine. We don't need to refresh our codebook. Definitely not this complex thing here. Again, remove the VQ loss. Let's clean this up here. No initialization of the codebook, using encoder outputs at least. And now the model returns only, well, it returns 4 values. So let's change that here. And these aren't even used. Well, the VQ loss can be removed from here. So basically we are just going to use the L1 loss. Well, the paper uses adversarial loss, perceptual loss, and alignment loss. For now, I'm just skipping it. In a later episode, after I cover adversarial generative networks, we will tune this up. So remove the VQ loss. This again removes these. We don't need to keep track of the VQ losses anymore either. Only the reconstruction loss and the perplexity. Also removing it from here. And the refresh codebook part, it's not needed anymore. Great. Let's keep the hyperparameters the same for now. I have a 50 epochs here, but I set the learning rate to half, so we can revert that. Perhaps best to remove this optimizer from here, so we always declare it in this code block. And let's go back to the quantizer. We don't need this anymore either. The encoder outputs the same. So a grid, 16 by 16 grid of d-dimensional latent vectors. There's no change there. I'm gonna restart my kernel, run everything before. And the new code. So first, let's take the distances and normalize it a little bit. So we find, so this is BHWK, so this stores the distances from all input latent vectors to all the latent vectors in the codebook. We subtract the minimum. That means the closest distance will be 0. And this way we can convert it to logits. If we write this, and tau is a constant here. The paper uses 0.07 based on their experiments. For me, in my experiment, 0.7 worked better, but feel free to adjust yourself and play around with it. So if we have logits, we can convert those logits into probabilities. With the softmax. And the Z ZQ, well, we won't have ZQ straight through anymore either. We will just have ZQ, because the fantastic thing is that we don't use torch.argmin anymore. So this is completely differentiable. Don't need to detach this, detach that, ZQ straight through, gradient flowing everywhere. Nope. This is the ZQ straight through, but we can call it ZQ. So the ZQ will be just props matrix multiply E. So I wrote lots of stuff, and let's just print the shapes of why this and why that and what looks how. So print dists. Let's always print the shape and then the value. So the second dist will be the reduced dist, so call it reduced. Let's print the logits as well. Let's print the probabilities. Let's print E as well. Now E is the codebook weight, a matrix, and we can print ZQ. Let's not deal with the perplexity now. Of course, these are the distances. We have 4 input vectors, let's say from the encoder, and we have 5 codebook vectors. So this has 4 rows, and these are the distances for the 5 codebook vectors each for the first encoder output vector. These are the 5 distances for the second encoder output vector, and so on. Now the second dists, we subtracted the minimum to have much lower numbers. We converted them to logits using this formula, and here the tau is a temperature parameter. Now, as I mentioned, the paper uses this 007 value because based on their experiments, this yielded the best values for them. Now, if the temperature is really low, maybe much lower than this, it means that the logits will become higher numbers. And so the probability distribution will become more peaky. And with a really low temperature, it would almost kind of work like an autoencoder, a non-probability one. So we converted them to logits, and then the logits can be converted further to probabilities using the softmax. That's what the softmax is for. And we perform that on dimension 1. So this is dimension 1. If you add these numbers together, then they will sum up to 1, each row. So this is the probability distribution for each of the 4 encoder output, and therefore the VQ input vectors. So we could say that there's a almost 21% chance that the first input vector will be the first vector from the codebook. And there's a 15% chance that it will be the second vector from the codebook, and so on. So these are the probability distributions for each input ZE. Now, these are well, it's the codebook itself. And this is one codebook vector, second codebook vector, third codebook vector, etc. And if you check the shapes of the probabilities, it's 4 by 5 and 5 by 3, which technically means that we can multiply these, and for these probability distributions, so this row, this distribution, which has 5 elements, will be multiplied with the first column in a dot product fashion. So it will be the dot product and multiplied element-wise and add that together. And so on as matrix multiplication goes. And we will arrive with a 4 by 3 shaped matrix, which contains the quantized vectors. And these are basically the expected values of that probability distribution. So with this matrix multiplication, you can calculate the expected values for each input vector given these probability distributions for each input vector. So this is completely differentiable. We don't need to keep track of the codebook and whatever and so on. So this is pretty simple, pretty nice. And also for the perplexity calculation, if you remember, we had to do one-hot encoding and such. But since we already have the probabilities, we don't even need to do that. We can calculate the average probabilities, probs.mean, on dimension 0. So if we go back, here are the probabilities. On dimension 0, print that out. Yeah, commenting it back. So we have the average probabilities of each codebook vector, a number for each. And since we have these, we can calculate the Shannon entropy right away. And the perplexity, again, is just the entropy exponentiated. I'm going to remove, or at least comment these out. So that's the core of it. Let's see if this works. No, I made some yes because so now our only loss is the reconstruction loss. Now training finished, and remember that in the last episode with the standard VQ-VAE, I trained it for around 300 epochs, and the L1 loss was fluctuating around 0.03. And now just after 50 epochs, the L1 loss is around 0.02, and the perplexity from 7 has grown to 278 without codebook resets, without encoder outputs, and we can see that the evaluation loss is also great. There's no overfitting. So this is a continuous latent space, and according to the paper, I will leave the link in the description. They use it with transformers. When applied to transformer-based architectures, our approach compresses 256 by 256 and 512 by 512 images using as few as 32 or 64 one-dimensional tokens. So our parameters D256 and K512 might be a total overkill. I'm not even going to train this any further. So recall this was the VQ-VAE's output after 300 epochs, and this is only after 50 epochs. So what I'm going to do now is lower the dimensionality and keep the codebook size and check how it changes the output reconstruction. Now I trained this for 150 epochs, and the results, the training loss is not so great, but it's still better, or at least on par with the standard VQ-VAE result, and the perplexity is 142. Now I started with a 4E-4 learning rate for 50 epochs, then halved it for 50 epochs and halved it again for 50 epochs. In this case, is the perplexity isn't growing enough, we can adjust the tau parameter. So I adjusted the tau from 007 to 07, and the perplexity started a little higher. Previously it started on 400 something, and it's a little higher, and this is normal in the case of the soft VQ because the codebook is initialized in a uniform distribution, and as the network started to specialize, then it will start to use less and less codebook vectors. Well, I can't really say that because it's a probabilistic model, but it's lowering, and I could train this a bit more, perhaps arrive at some good enough results, but for some reason, because this doesn't go as low as fast as when we had the dimensionality to, I think it was 128 or 256, and it makes me think that, so D is 3 here, and the encoder outputs then 16 by 16 by 3 tensor of information. So that's just probably not enough numbers for the model to be able to reconstruct that image. So the bottleneck is too thin. So let's keep the tau, let's keep it at the original value as it is in the research paper, 007. Increase our latent dimensionality to 16 probably, but I would also try 8, and train the model. So I trained this for 100 epochs, and as you can see, it's already at 0 to 36 with 145 perplexity, meaning we could even lower the codebook size to around 200 or so, or even less, and still arrive with a better reconstruction quality than the normal VQ-VAE. And it's just with an L1 loss. So if we add perceptual loss and GAN loss, then I'm pretty sure we can improve this radically. So this is it basically. Feel free to read the research paper because there's many more to it, but this is the core, and I think it's just fantastic. I mean, all the hassle with the VQ-VAE, and now this is soft version. You can just delete half of the code, no messing around, and yes, it's a continuous output in the latent space. It's a continuous distribution. So I will need to actually research how the transformers work with it. But I think it's just much simpler, much faster, easier to train, less parameters, and it converges much better. So that's it. See you next time.